What you are about to see is a video presentation of a collection of software in the new S system for dealing and building regression and classification trees. My name is Darryl Pregobon. I'm one of the authors or co-conspirators of this software. The video presentation will run through roughly 5 or 6 view graphs showing you part of a graphics window and also part of an S window. We will briefly be outlining the functionality of the system and then followed by 1 or 2 short examples. The software itself is somewhat unique in this area in that it decouples growing the algorithm used for growing a tree from other algorithms or methods for displaying trees, for diagnosing them, for simplifying them, modifying, and predicting from them. For growing a tree, we have 2 basic functions. The first, called tgrow, is one you'll see extensively in the sequel, and in its simplest form takes a single argument, a model expression, which contains the data to be used for this particular example. The second function, called tedit, allows you to edit the split of a given tree and regrow the tree from below. In both cases, the output of the functions are again trees. The second collection of functions are special functions for displaying trees. The first function, tDisplay, will display a tree in tabular form. The next function, tplot, is the one you'll see the most of, and it displays it in graphical form. tpick is a particular function for displaying a tree in graphical form, but using a special device driver for the pick preprocessor to trof. And tlabel is an interactive program that allows you to label a plotted tree on your terminal under mouse control or interaction. For diagnosing a tree, we have special tools, mostly to be used interactively, for inspecting the contents of a tree, tinspect, for identifying the observations in individual nodes, and another function called tburl, which allows you to look at the competition for the best split at any given node in a tree. tburl is used most effectively with tedit, so once you find a split that, although is not optimal, is perhaps preferable on other grounds, you can edit that tree and then reburl or do whatever you would like. There are several functions for simplifying a tree, one graphical and one not. tsnip allows you to interactively snip off branches of a tree, where tprune is an implementation of Bryman, Friedman, Olshan, and Stone's cost complexity pruning algorithm. There are several functions for modifying trees. tselect allows us to select subtrees of a given tree. You can select one or more. It will construct a data structure of all of these trees. Shrinking is a competitor to snipping or pruning a tree, which smoothly changes the cell estimates toward their parent. And tgraft allows you to graft on a subtree to an existing tree. And finally, we have several functions for predicting from a tree. tpred will give us a list of predictions, and tdrop, which will give us those same predictions, but in the form of a tree itself. The first example I want to discuss to you is an example dealing exclusively with continuous variables. It's an example dealing with trying to come up with a formula for predicting the mileage of an automobile given its weight, its length, its cubic inch engine displacement, and the gear ratio. And this data set comes from the standard set of data sets with S. The single function to grow a tree will take one of these model expressions, which names the variables to be used and also knows about their type, and implements the recursive partitioning algorithm and assigns the result of this algorithm to a data structure Z. Now Z contains all the details of the tree construction, but hopefully you never have to look at it in that form. That the other functions are used for displaying it in a more pleasing form. tplot, for instance, is dedicated solely to looking at a graphical rendition of a particular tree. Now, given that we have a tree, you can see clearly that the first variable it's split on to predict mileage is weight, saying cars with weighing less than 2,365 pounds go to the left, and those greater than 2,365 to the right, and the next best splits are also on weight. Similarly, length starts coming in, and length is of course highly correlated with weight, so these are mainly size characteristics of the automobiles. And then engine displacement comes in somewhere far lower, and gear ratio would come in once over here. Given we have a tree, we can do things to it like we would expect to do in regression settings. We can get predicted values from this tree, and we can compute residuals likewise. We have a slight bug here in the device driver, so I'm going to have to call this to a halt, and we'll pick it up in a minute. Well, maybe we can get around it. I think I actually have Y-hat lying around. So let me just try this and see if we can salvage this demo, at least for a little while. Okay, so anyway, what you're seeing here is a QQ plot of residuals. I basically used the function tpred to compute fitted values. I then subtracted them from the Y variable to get residuals. And a QQ plot of residuals is something we'd expect with any model. Another function we have plots the within cell means versus the within cell variances. And in particular, you see in this particular plot that there is one node number 4, which is both the largest, has the largest node variance and the largest node mean. We can find out which observations correspond to that cell by simply asking for it using tidentify. And given that we have it, we can then display that data itself. And we see, for instance, that these are the automobiles that ended up in the node number 4, and this is the observation number in this column. This is the name of the automobile, and here is the value of Y, that is the mileage. And you see all of these are fairly in terms of range in the high 20s and low 30s, with the exception of this Volkswagen Rabbit diesel, which happens to be the only diesel in the study. And so for this reason, perhaps we can just investigate what it would be like to delete this Volkswagen, this diesel from the study and continue. We can do that simply by creating a new model from our existing model. By deleting out of the 74 observations, deleting the 71st one. And that would be the S expression used to do that. And then we can create a new tree simply by calling tgrow on this new model expression. And we've now called it Z1. And here we are at this point where we've now grown, we've deleted an observation from the model, and we've regrown the tree, and we've plotted it with these three statements. And you see now that displacement has crept up the ladder for these small cars. Weight and length still play a large role for the other cars. We can alternatively, or in fact, we can just as well look at this mean variance plot for this new tree, because again, all we have is a tree structure. We again see a particular cell, that's the node that sticks out, and perhaps this is indication that the tree itself exhibits non-homogeneous variance. So we could explore transforming Y, say for instance from miles per gallon to gallons per mile. One way we can do that is using a tool M-augment, which just means we're going to change our model by making a new Y variable 1 divided by the old mileage. We can grow a tree to these new data simply by saying tgrow, and we can plot the tree likewise. The severe overplotting you're seeing is due mainly to the fact that the display, to get reasonable resolution on the camera, had to be somewhat compacted. And you can see once more that it took simply 3 steps to change the observation from Y to 1 over Y and regrew the tree. Finally, since there is such large size components in these data, let's look at first doing a least squares regression using the variables in this model. So I've just assigned to the data structure ZReg the value of a least squares regression to these data. And let me construct yet one more model if my fingers will cooperate, which changes the Y variable at this point to the residuals from a linear fit. And you see at this point that the tree has changed very dramatically, that effectively weight is missing from the highest levels of the tree, and it comes in much lower, explaining or indicating that the regression, that the size variables have been for the most part accommodated by the regression, and what's left in terms of interaction is in terms of the displacement and gear ratio, if these are at all significant. I will show one more function with regard to these data before we move on to our second example. This is a function which allows us to interactively inspect the contents of the nodes of the tree, whereby by pointing to a particular node we get the distribution a la a histogram appearing on the screen. So this is the histogram of all the data in the Y node, that is in the root node, that is the overall mileage. For the light cars, we see the histogram is to the right, whereas for the heavy cars, the mass of the histogram is to the left, indicating lower mileage for heavier cars. And we can conveniently move around the entire tree, so we see not only the mean of the node, but the entire distribution of the data at that node. The second example concerns one from speech recognition, where all the variables in this case are categorical. That the variable of interest, the dependent variable, is the occurrence of a period in a piece of text, and we want to know if that denotes the end of a sentence or not. And to predict that, we have the following covariates: whether the word immediately previous was an abbreviation, whether the next word was capitalized or not, what part of speech the next word was it a pronoun, a proper noun, a common noun, and finally, was there any intervening punctuation between this period and the next word. Now we can grow a tree to these data in much the same way we did before, by simply saying tgrow of mod s. And note that we did not have to indicate to tgrow that we were growing a classification tree here as opposed to a regression tree. That information is carried in the model expression and then transmitted to the tgrow function. So it makes it very easy for the user interface. In this particular case, we see a very shallow tree. There are about 400 observations in all. The primary variable it's split on is the abbreviations, and no going to the left, and yes, it was an abbreviation going to the right. And there's a bit of overstriking here, but this happens to be a node of perfect prediction. Whereas the rest of the variables looks at the next word, part of speech, etc. Now, one thing we could do to this tree, for instance, is call the function tsnip, which allows us to interactively examine whether snipping off a particular node of a tree will be useful or not. What tsnip allows us to do is move around the tree structure, and it's sort of a what-if style of analysis that says, if we snip off this branch here, how will the total deviance or impurity of a tree change? And it says it changes that in the whole complete tree you have something around 10, whereas if you snip off this branch it goes all the way up to 20. If we snip off this branch, oops, I think we snipped it off. If you click twice on a node, it actually removes it. Whereas if you only click once, it doesn't remove it. So snipping is a way to interactively and subjectively browse a tree and perhaps simplify it. Another tool is tselect, which allows us to select subtrees from the given tree. And this allows us, again, to point to a particular node and select it and assign it. So I can plot this subtree now, and you note that it is just the right-hand branch of the previous tree, but it is in fact a tree itself, so we can do to it what we can do to other trees. Another way to look at a tree is in the semi-graphical form, which uses indentation as a means of a tree. And because of a screw-up in the device driver with the spacing, we can't see exactly what I intend to show. But essentially, this is a rendition of a tree which contains a lot more detailed information. And if you were just printing this at a terminal, rather than trying to trick a device driver to do it, you'd get a much clearer picture of what this was all about. Another alternative to simplify a tree is called shrinking, which doesn't change the overall structure of a tree, but does change the predictions in a tree. And so I'm now plotting this shrunken tree, and the shrinking is such that the values occurring in the root nodes are shrunk to their parents, recursively to their parents, all the way to the node. The net result, for instance, we can display as follows. So what I'm going to be listing out is the actual probabilities now associated with these nodes. And again, it's slightly hard to see because of the spacing. And these are the values of the subtree itself, and these of the shrunken subtree. And you see that effectively no pure nodes remain. That is, this is a type of smoothing procedure which, if you don't believe that a node is pure and you only happen to observe it in your data, the method of shrinking will always put some non-zero probability in each node. And this may be an important alternative in applications where interpretation isn't that important, but ultimately high-quality predictions are. Once you have a tree like this, what you can do is then graft it onto the tree we originally started with, and we can do that simply without going through a lot of the motions. Take this shrunken tree, graft it onto the original tree, and in fact, remember what we've done is we selected this subtree and we then shrunk the fitted values, and graft allows us to paste it on. And what we've accomplished in this case is, because this was a particularly good split, so that anything following an abbreviation is definitely not a period, we did not want to change that because that is a valid grammatical rule. We did change these because there was less motivation to keep those the same. So that concludes, for the most part, what I intend to say, and I leave you with a little bit of reading on the nature of trees, as was the case in this past century. Thank you.